Your Java service is getting killed. You look at the pod spec, and there is clearly headroom in the memory request. So why is the kernel killing the process? That is the scenario interviewers put in front of mid to senior candidates all the time. It sounds like a simple resource problem, but the real answer requires understanding two memory models that are operating independently of each other: the JVM Heap model and the Linux container memory model. If you cannot explain the gap between those two, the interviewer knows you have been lucky rather than careful in production. Let me walk you through why interviewers ask this: the mental model you need, a concrete walkthrough with real numbers, and then the wrong answers that will cost you the offer. First, why do interviewers care about this particular scenario? Because kills on JVM workloads in Kubernetes are one of the most common production fires that teams do not anticipate. When a candidate understands this problem deeply, it signals several things at once. You know how the JVM allocates memory? You know how C groups enforce limits. You understand that those two systems do not automatically speak to each other. And you know what to do about it operationally. That is a lot of signal in one question. Interviewers at companies running Java microservices at scale, think financial services, large e-commerce, SaaS platforms, they ask this almost as a screening question for senior SRE and platform engineering roles. Now here's the mental model you need to hold in your head. The JVM has its own memory manager. It carves off a chunk of native memory from the OS at startup for the heap, and it has defaults for how large that heap should be. For a long time, the JVM's default maximum heap size was 1/4 of total physical memory. If you had a node with 32 gigabytes of RAM, the JVM would happily try to claim 8 gigabytes as its max heap, even if you told Kubernetes to give that pod only 512 megabytes. When you containerize that service, the Linux kernel enforces a memory limit via C groups. The C group says this container cannot use more than, say, 512 megabytes. The JVM does not know about that limit by default. It sees the node's total memory. It sizes itself accordingly. The heap grows. The process crosses the C group boundary. The kernel's out-of-memory killer fires. The pod is gone. And your pod spec memory request of 512 megabytes looked totally reasonable. Here's the key insight. The kill does not happen because your request was too small. It happens because the JVM was never told what the container limit actually is. Now let me get concrete. Say you have a Spring Boot service running in a pod with a memory limit of 768 megabytes. You check the pod spec and everything looks sensible. The service handles a moderate request load. After a few hours, or after a burst of traffic, the pod gets killed. You exec into a running pod and check what the JVM thinks its maximum heap is. You can do this by running the Java command with the XX print flag's final flag and grepping for max heap size. What you find is that max heap size is set to something like 2 gigabytes because the JVM read the node's memory, not the container limit. Every time the heap tries to approach that 2 gigabyte ceiling, the C group cuts the process down long before it gets there. The first fix most engineers reach for is setting the XMAX flag explicitly. In your container command or in an environment variable, you set something like -XMX 520 to cap the heap at 512 megabytes. That is better than nothing, but it introduces a new problem. You have now hard-coded a value that you will have to change every time you adjust the container's memory limit. You have also not accounted for the non-heap memory the JVM uses. This is where the interviewer wants to hear you talk about Java's container awareness. Starting with Java 10 and backported to Java 8 Update 191, the JVM ships with a flag called UseContainerSupport. In modern JVM versions, this flag is enabled by default. When it is on, the JVM reads the C group memory limit instead of the total host memory. So if your container limit is 768 megabytes, the JVM now knows that number and uses it as the basis for its default heap sizing, which is still going to be around 1/4 of that limit by default, so roughly 192 megabytes of max heap. But here is where the trade-off lives, and this is what separates a good answer from a great one. The JVM does not only use heap memory. You have the heap, but you also have the metaspace, which stores class metadata and can grow unbounded by default. You have the thread stacks, one stack per thread, typically 512 kilobytes to 1 megabyte each. You have the JIT compilation buffers. You have the garbage collector's own internal data structures. You have direct byte buffers if your service uses NIO or Netty. All of this is off heap, native memory, and it counts against the C group limit just the same as heap memory does. A classic failure pattern that teams run into is this. They set XMX to 80% of the container limit, feel good about themselves, and then get killed anyway a few weeks later when load increases, thread counts go up, or a new library starts using more metaspace. The remaining 20% was not enough to cover the JVM's non-heap needs under load. So what is the right approach? The pattern that holds up in production is to set both a maximum heap and a maximum metaspace explicitly, and to leave a buffer for native memory that you size based on what the service actually uses. A common starting point for a service with moderate thread counts and no heavy native library use is to allocate roughly 60 to 70% of the container limit to the heap via XMX, cap metaspace with XX max metaspace size at something like 256 megabytes for a typical Spring Boot app, and then make sure the remaining headroom covers thread stacks and any native buffers. For a 768 megabyte container limit, that might look like setting XMX to 400 megabytes, max metaspace size to 256 megabytes, and accepting that you have about 112 megabytes for everything else. If that is not enough, you either reduce thread pool sizes, reduce max metaspace size if you have profiled and confirmed the class count is low, or you increase the container limit. The other side of this that the interviewer may probe is the relationship between requests and limits in Kubernetes. Requests are what the scheduler uses to place the pod. Limits are what the C group enforces. If you set a request to 512 megabytes and a limit of 768 megabytes, your JVM with UseContainerSupport will size against the 768 megabyte limit, but the pod could be scheduled onto a node where other pods have also overcommitted. If memory pressure hits that node, the Kubernetes will start evicting pods that are using more than their request. Your JVM is almost certainly using more than 512 megabytes in normal operation if you sized it against 768, so you may get evicted even without hitting the OOM killer. This is why experienced engineers often recommend setting requests and limits to the same value for memory on JVM workloads in production. You give up the flexibility of overcommit, but you get predictable scheduling and you avoid eviction surprises. The JVM's stop-the-world garbage collection pauses already make these services sensitive to resource contention. You do not want the added chaos of running on a node with noisy neighbors competing for the same physical memory. Another wrinkle worth mentioning is the GC algorithm. The G1 garbage collector, which is the default from Java 9 onwards, has its own internal region sizing and background thread behavior. If you switch to ZGC or Shenandoah for lower pause times, those collectors tend to have higher native memory overhead. That changes the headroom calculation. You should profile actual native memory usage with tools like native memory tracking, which you enable with XX native memory tracking, set to summary or detail, and then use JCMD to dump the breakdown. That gives you real numbers instead of guesses. Now let me tell you the wrong answers that candidates give. The most common wrong answer is, just increase the memory limit. That is not an answer, that is a workaround. It delays the problem and costs money. Interviewers want to hear that you understand why the kill happened, not just that you threw more RAM at it. The second wrong answer is saying, UseContainerSupport solves everything. It helps, but as we covered, it still leaves you exposed to off-heap growth if you do not account for metaspace and native memory. The third wrong answer is treating XMX and the container limit as the same number. Setting XMX equal to the container limit will absolutely get you killed, because the heap is only part of what the JVM needs. A fourth wrong answer that senior candidates sometimes give is focusing entirely on tuning without mentioning observability. In a real interview, you want to say that you would instrument the JVM with metrics, expose heap usage, metaspace usage, GC pause times, and native memory tracking through your metrics pipeline, and you would alert before you hit limits, rather than waiting for the kill to tell you something is wrong. That shows production maturity. Let me give you the 30-second recap.